Hey everybody, welcome to another mini lecture in complex analysis. In this one we are going to talk about one of the ways of making sure that the function you have at hand is holomorphic. Well, as you know, in complex analysis we have a lot of theorems about functions that are holomorphic, but we don't have so much to say about functions that are not. So we would like to make sure that the functions we're dealing with are indeed holomorphic. And what I'm going to show you is one of the ways to make sure. And by the way, this is the English version of a video I've previously posted in German. So if you prefer to watch this in German, you're free to do so. The link to the German version is in the link below. And now let's get into things. So let's imagine we have a function f of z. So this is a function of a complex variable z. And this function f is defined on a simply connected domain U. So let's write this down. So this is simply connected. Right, which means the fundamental group is trivial, or you can shrink every loop to the constant loop. This is what simply connected means. And so we have this function f, which is defined on U, which is of course in the complex plane. And you would like to establish that this function f is holomorphic. And now what you do is you look at a sequence of functions of which you know that they are holomorphic and which converge to your function f. And they do so in a special kind of way, namely they do so uniformly. So we look at uniform convergence of a sequence of functions fn to a function f. And this will allow us to conclude that f indeed is also holomorphic. And this is done as follows. Imagine you have some kind of contour C in the complex plane, and you parameterize this C by some parameterization P. So you can integrate around this contour C in this fashion, so that you can write the integral over C of fn of one of the functions in your sequence of functions is the integral from a to b of fn px, the derivative of px dx. So this is just writing out the complex integral of the function fn around this contour C using this parameterization px. And this allows us to reduce this task of integrating around the circle C to the task of integrating over an integral over an interval a to b. So this is the closed interval ab, which lives inside the reals. And now what we do is we remind ourselves of Cauchy's theorem, which says that if you have such a closed contour C in the complex plane and you're talking about a simply connected domain, which in particular means that every holomorphic function, such as our fn, has an antiderivative, then the Cauchy theorem tells us that such an integral is always zero. So this integral of the function fn is zero around this contour C. and for that matter around every closed contour C in U. And now we can express the integral of the limit function f as the limit of integrals of functions fn. This is because we are integrating over a bounded interval, a closed interval, a to b, and because we are assuming that the sequence of functions fn is tending towards f uniformly. So this is what allows us to do this operation here of expressing the integral of f as the limit of integrals of functions fn, which tend to f. And of each of these integrals in this sequence here, we know it's 0. This is what I've just said a minute ago. This was Cauchy's theorem. So we can conclude that for every contour C, the integral of our limit function f around this contour is also 0. And now we invoke another theorem we have previously proved on this channel, which is Moreira's theorem. And Moreira says if you're talking about a simply connected domain and you have the feature that your function's integral around every closed contour, such as our C, e.g., is 0, then your function is already holomorphic. So we're done. We have proven that given that we have uniform convergence of the sequence of functions fn to f, we can, well, do this little trick, and we can use Cauchy and Moreira to conclude that f indeed also is holomorphic. So this is what I wanted to show you. This is one of the tricks to prove that a function is indeed holomorphic. So thank you for watching. If you would like to see more about complex analysis and math in general, please don't forget to like and subscribe to this channel, and see you next time.